topic by topic. We are looking at centripetal motion, and particularly today we're going to concentrate on centripetal acceleration, or angular acceleration, or centripetal acceleration, because basically if we're traveling in a straight line, life is easy. We might be going at a constant velocity, and constant velocity simply means we are basically moving at the same speed in a particular direction. But as soon as we go onto basically a sort of circular system, things change. You see, if we take ourselves a nice circle going along here, basically, although I may have a velocity v here, by the time I get to here I've got a different velocity. I may be still doing the same speed, but I'm doing it in a different direction, and this causes problems. So we measure things like angular speed here as angular speed, and that is simply our angle we turn through in the time taken. So we're going here through an angle of theta, and we're measuring theta is measured in radians, and we chose to use radians because it's easier to try and work in radians. We also worked out, if we know the time period, we know that my angular speed can equal either 2 pi over the period, or we can work out that it works as 2 pi times the frequency. Linking velocity, we got last time v equals r. There we go. So as the linear speed increases with the radius, and if we look at an example of this, we might look at an example of perhaps something like the minute hand of an analog watch. Let's suppose this, let's do a clock. Looking at my clock, it's about 10 centimeters long, so let's say that the minute hand here is equal to 10 centimeters. Right, so let's see if we can work out its frequency. Now, what's its frequency going to be? Well, I know that t equals 1 revolution, and that equals 1 hour. So it's going to be 60 times 60 to get it into seconds, which is going to give me 3,600 seconds. And what we want to work out then is my frequency, which is 1 over t, which is going to be 1 over 3,600. And to work that out, then all I'm going to require is my calculator, and we can work out 1 over 3,600, and that's going to give me, unhelpfully that, but more helpfully we're going to get here 2.7 here, let's call it 2.78 times 10 to the minus 4 hertz. What's going to be my angular speed? and my angular speed here is going to be 2 pi times the frequency. So we're going to have here 2 pi times my 2.78 times 10 to the minus 4, and since I've got that number there, we can simply multiply this by 2 and pi, giving me here an answer of about 1.75 times 10 to the minus 3 radians per second. If I want to try and work out the linear speed at the end here, so my linear speed is going to be V equals R omega. We've got the omega, so we've got my radius, and we've set my radius here at 10 centimeters, so that I want in meters, so that's going to be 0.1 times 1.75 times 10 to the minus 3, and that we don't really need a calculator to do, but we're going to do it anyway, and I'm just going to times that by 0.1 to give me 1.7 times 10 to the minus 4. So we've done some simple calculations working out simple things about speed. But how about acceleration? What do we know about acceleration? As I said, the velocity is constantly changing, so therefore we're basically always accelerating. So we are basically accelerating at a constant speed. Which does seem rather daft, I suppose, in some ways. And what we're going to do is we're thinking of this as either angular acceleration or maybe we could call it centripetal acceleration. And we know our acceleration is going to be the rate of change of the speed with time, and we know this to sort of work out it's going to be basically the speed squared, which we're going to call v here, v squared over r. Now, since we know that v equals r omega, then what we can do, we can write this slightly differently. We can say that's going to be my here acceleration is going to be r omega basically times r omega all over r. Well, those r's can cancel, which is going to give me simply acceleration is r omega squared. So acceleration here is a vector quantity, and that gives me a problem because it's a vector quantity, but basically the acceleration is always in the same direction. If we think about this, That's not surprising, because wherever I'm going, my acceleration is always towards the center of the circle. So, how about this for an idea? We've got a car travelling round a bend. The bend, we're going to give this a radius of, let's say, 50 meters, and we can have the car moving at a speed of, I don't know, 5 meters per second. So let's work out that our acceleration here is v squared over r. So we've got my acceleration equaling 5 squared over 50, and you'll see that I chose my numbers wisely, because that's going to give me 25 over 50, which is simply going to give me 0.5 meters per second per second. So that's this idea of centripetal acceleration. Now, if we're going to do that, then we can also work out there's going to be something here to do with a force. And our force, we know, equals the mass times the acceleration. So we can work out then that my force now equals mv squared over r, and we can say that also the force equals m r omega squared. So we can work out quite a few things using this. Now, what else can we do with this? We can start looking at this idea, and this idea of centripetal force is quite interesting. I know when I talk to some of my students, they talk about a centrifugal force, a force throwing them out. It doesn't exist. It's a force attracting you in, and it doesn't seem obvious really when you start trying to do this, but it does make some sense. Let's suppose the example we chose in the last lecture, which was we're moving basically in a circle, and at any time you might let go, and if you let go you carry on in the direction that you were traveling. You feel like you're being thrown out that way, but in fact we look at the physics, and if you're here and you let go, this is the direction that you go in. It's just really you not believing in your senses, the way that it works. And we can see this by looking at a very simple little experiment. And let's have a look at a very simple experiment. And what I've got here is my Hot Wheels track, and what we're going to do is the classic. I've got the loop, so we're going to come down here. we are going to go then round loop the loop, and amazingly the car will stay at the top there, and we know that it does. I'm going to leave you watching that little bit. I'm going to release the car at 3, 2, 1, go, and I'm pleased to see that it failed miserably. What happens quite often with my Hot Wheels track is that if I set it up and leave it too long, it sort of makes a too bendy joint, too rigid. It's probably that one that I need to sort of also undo. So we'll try that one again, just linking it up. Sometimes preparing these things not necessarily worth it. We'll try again. 3, 2, 1, go. And we got the car going round. And
oh, it's a bit quick, was it?
Okay.
Let's see if I can slow that down a little bit. And
here it is.
And we can see there is the car literally hanging on upside down. And the only thing that's holding that in place is basically its speed.
Let's try that one again. And I'll show you what I mean. What I'm going to do is forget to press the button so you see me, but you can now do that. Right, we're just going to let the car go at full speed. Yep, we'll have another go. Never seems to work well on live TV. Here we go. Hopefully you got that. If you didn't, let's try it again. And there it goes round. Now this time what I'm going to do is we're going to take the car with a lower velocity, and I'm only going to take it halfway up. It's still above the height of that circle though. Here we go. And it just about made it. Bit poorly, but we'll try it again at the same place. And it just nearly makes it, but as you watch it going round there, not quite enough to hold it. Whereas if we have it lower, then this becomes basically pathetic. Because it's just not got enough to try and do anything to it. So it's interesting trying to have a look at how the car sort of tries to behave as it goes round. One thing that we do notice when we look at this, it looks interesting. I'll show you why. I've got it from here, another angle, and as the car comes in and goes round, we can see the amount of movement. If you watch that thing, that's showing there's a fair amount of force being put into this bit of plastic. And so we're actually losing quite a lot of force there. And the way of trying to improve that is of course to sort of fix the track so that it doesn't move as much. Having said that, when we do fix it, we still find the track at the top here wobbles quite a lot, and that's due to the force of this vehicle going round. So a good fun experiment that we can actually do to try and prove that sort of we can get a car upside down working, as long as you've got the faith to sort of keep your foot on the accelerator. And the same sort of thing works when you take a car around the famous Brooklands racetrack. The racetrack here has wrong camera. Let's just go on to the right camera. The Brooklands racetrack is curved, so the cars in the old days used to go round, but as they got faster, so they could actually move further up the track, and as they got further up the track, then they could actually go faster, because instead of a force throwing them out this way and trying to topple the car, the force was that way, and it was keeping the car upright, so the car could go faster. And trying to show off now, when I took the Le Mans Jaguar out for a little spin, I could manage to keep it up at around about 220, 230 miles an hour, simply by keeping it on a parabola. And that was at Vauxhall's Proving Ground, which was quite nice day out to go and try Le Mans Jaguar. And good fun it was too, but it was all physics, and that's the interesting thing, how all of this stuff is really physics. Okay, so we've got this idea of centripetal acceleration, and we've got this moving in vertical circles. So let's look at this vertical circle. Now, what's actually happening? Well, we've got our car at the bottom as it comes in. We've got our car as it's going up, and we've got our car as it's travelling literally upside down. So let's see what we know about this. Well, we can say that the mass of the car, well, that's going to be constant. We know that gravity, well, that's going to be constant as well. So the contact force, however, the force pushing outwards here, well, if you like, the force doing that, that's going to vary as this car goes around this circle. So let's have a think about what happens at the bottom. Well, at the bottom, the weight is going down, but if we think about our contact force here, it's in the opposite direction. So we've got this centripetal force. We've got this force going towards the centre, and technically I suppose at the bottom it's not going to be affected at all. It's going to happen more as it starts going round. But we've got a contact force, a centripetal force, going in the opposite direction. So we can say that this R at the bottom minus the force of gravity is going to be mv squared over r. And we remember what mv squared over r was. This is our centripetal force. Now, at the side, what's going on here at the side? Well, we've got a force coming in here, and we've got this, if you like, mass and gravity going that way there, acting at 90 degrees to one another. There is no component here doing anything, so our contact force here is just going to equal mv squared over r. And at the top, both the mass and gravity and the contact force are both acting downwards towards the centre of the circle, and together they provide the centripetal force. So R at the top here, we're going to add mg, giving us the mv squared over r. So you can see the contact force at the bottom is much larger than at the top. At the bottom of the loop, if you're in the car, you would feel a force pushing you down. Now, as long as the ride is fast enough, it's really impossible for the car to go wrong. But what happens when it slows down? Well, as we saw, the centripetal force here is smaller. That means the contact force is going to be smaller with the track, and if it drops down to zero, you just make the loop. And if it's anything less than that, then the car falls out of the sky and crashes. So we can use this, if we want to try and work out all sorts of forces for roller coasters and all sorts of other things. And if I were in my favourite job, then probably it would be designing a roller coaster. And if I was trying to design a roller coaster, unfortunately this requires some physics. Yeah, it's not just making it look good. It's not like playing around with Lego and Kinex and other things making roller coasters, but instead we've actually got to do some physics to make sure basically that our passengers are going to survive. So if I've got a roller coaster and it's going to do a loop-the-loop, so let's give ourselves a loop here, then we've got to decide on some sort of radius here, and it's got to be something reasonably big, I guess. Let's go for about 12 meters. Right, so how fast are our cars going to go round there? Well, I don't really know, so let's have a look at a guess. Let's say we're going to go for 15 meters per second, and let's see if we can work out what the centripetal force on a typical passenger is going to be. So let's take our typical passenger and let's give them a mass, let's say, of 60 kilograms. So let's work out what we've got. Simply, our force here is going to be mv squared over r, which is going to give me my mass, 60, times 15 squared over 12. And for this we're going to need to do a calculation. So let's go over and do a calculation, which is going to be 60 over 12, and the 60 we're going to multiply by my 15 squared, and that's going to give me here 1125 newtons. Right, so let's see if we can make things easy. So gravity we know is going to be here at my ride, it's going to be 10 meters per second because I like that. Or if you prefer, we could actually think of this as 10 newtons per kilogram. So the passenger mg is going to be 60 times my 10, which is going to give us 600 newtons. So from what we worked out at the top, my contact force at the top was added to mg, and that equaled mv squared over r. So my contact force here plus my mg, which was 600 newtons, equals 1125 newtons from up there. And so this is going to give me my RT, which is simply going to be here my number 1125 here minus my 600. And since I've got that on the calculator, there is our 525. So that looks okay. Let's see what's going to happen at the bottom. Well, at the bottom we've got our B for the bottom, and it's going to be minus mg equals mv squared over r. So what I've got for that one is RB is going to equal my force 1125 this time plus my 600, and that's going to give me my 1725 newtons. So we've got those. So at which point in this loop will the passenger in our little car feel the heaviest? And that is going to be at the bottom. At the top, this is where you feel your stomach is actually sort of flying. So how about working out what is the minimum speed here that we ought to be trying to sort of go around this? So let's take my RT at the top, and that's going to be plus mg, and that's going to equal mv squared over r. Well, let's see, we've got those. RT is going to equal 0. Then what we've got mg equals mv squared over r. The m's on the same side cancel out. So rearranging that is going to give me v squared is going to equal basically rg. So what we've got here is going to be my radius, 12 meters, times my force of gravity. So that's going to give me v, which is the square root of 120, which is going to give me about 11 meters per second. I wouldn't like to live on the difference between the 1 and the 0 here. Right, so basically there is an idea of moving in simple circles about what we do. Now, we've also got something else with playing around with circles, and I thought we'd just like to have a quick look at this one. And this one is a little bit different.
Rather than this track this time, what I've got is a string suspended from the ceiling. And I'm just going to move the chair out of the way. And what I'm going to do is put a weight on there, and you'll see that we're going to do quite a lot on these sort of weights hanging. Now what I'm going to do is I'm going to give this a little spin in a circular motion, and hopefully it's going to stay like that. And when we make various oscillations of these things, we find that probably some of the safest ways of doing this, I'm going to come this side so you can see it perhaps a little bit easier, is rather than make a pendulum which just goes from one side to another, what we can actually do is we can take here a conical pendulum. Now, if I'm looking at this conical pendulum, we need to wonder about how it's working and what it's doing. So previously I've got up and I've measured the angle I can get to get this sort of circle in about this diameter, and that's about 6 degrees. I'm going to move this before I clonk myself with it.
Let's have a look at something about a conical pendulum. So let's get you to have a look at the conical pendulum. Right, so it's a pendulum, but instead of moving left to right, it's actually going to move in this circular pattern. And what we can do with this is we can measure that angle, and for me that's around about 6 degrees. basically I'm not trying to move this too fast. We've got some sort of force here, some sort of tension force going up, and we'll have the force of gravity of this mass pulling it down. And what we do need to know here would be here simply my radius. Now as this goes on, so the angle is going to gradually move down, and so the radius is going to gradually get less and less. But these pendulum or pendula work better than ones that go just forward and back. The ones that go forward and back, they do get smaller each time. These are much better if you want something like a smooth timing mechanism, and these are often used to calibrate the tracking of sensitive telescopes that move very slowly against the Earth's rotation to ensure that they remain fixed on that certain point in the sky. So we can try and do this to work out what's going on. The horizontal component of the tension here, Ft, basically is going to enable us to work out all sorts of things. It provides, if you like, this centripetal force F required for this circular motion. So we know that F equals mass times acceleration, and we know that also equals mv squared over r. We've also got our angle, so we can see that my tension here is going to be the sine of my angle is going to equal mv squared over r. That's the horizontal component. For the vertical component of this force, it's going to be cos theta, and that will simply equal mg. If we divide the first equation by the second equation, and since we know that the tan of an angle equals sine over cos, what we get is v squared over rg, and from that we can work out that the angle of the pendulum is not affected at all by the mass of the pendulum bob. This is quite interesting. So there gives us some ideas about centripetal acceleration and a couple of other experiments thrown in for good measure. I hope you found this useful. If you did, then please subscribe, give us a thumbs up, and I will see you next time when we do some more A-level physics, topic by topic. Until then, stay safe. Bye bye.